8 is the power 2. So let's just do this one first. So the 8 becomes 2 to the power 3. And then you multiply exponents, exponent becomes 6x plus 9. Bring this side down over here. Once you have it so you have two power forms with the same base, then you just set the exponents equal to each other, and it's easy. Subtract x, you get 5x. Subtract 9 from both sides, you get negative 10. So x turns out to be negative 2, and you're done. That's the easy kind of problem. You go back to the previous example, you can't do that. 5 is not a power 2. And I told you, one thing you can sometimes do is rewrite the thing as a log. That doesn't work out well here. So rather, I'm going to just take log of both sides. And I'll use natural log. So I'm going to do natural log of the left side equals natural log of the right side. And once again, you can do that. The rule says simply that if you have two things are equal, then log of those two things will also be equal. But once you have log of a power form, you can do what with the exponents? Yes, there. That's what I was looking for, even. Making factors. How am I messing this up? And seriously, like here, the 3 is the only part that's multiplied times log, which is wrong. It's supposed to be the whole exponent that's multiplied. All right. Now what? That's coming. Clean it up. Simplify it. In this case, you distribute. So multiply natural log of 2 times both of those. And distribute natural log of 5 on the other side. Now that it's all simplified, you have individual terms. What's the next step? Collect all the x terms together on one side. Yes. Let me do that. So this x term stays here. This x term becomes a minus 2x natural log of 5. The non-x term that was over there stays there. This one goes to join it, so it becomes positive. And we did all that because what did it gain us? What do we have on the left now? Hayden, what do you see? We have a common factor of x, which we should do what with? Factor it out. See, if you remember why we're doing this, you remember what we did. So we collect everything together, so we had a common factor, so we could factor out. So we do what last step? Yeah. And it's messy, but you have this whole thing multiplied onto your variable, so just divide it all away. So you get this that was on the right, divided by that whole mess. All right, now, let me say again, you cannot cancel anything in that expression. Top and bottom both have natural log of 2, but there's not a factor of natural log of 2. So you can't cancel it. Natural log of 5, you can't cancel it. If I were to erase that plus sign and the minus sign, so everything's multiplied instead of added or subtracted, then I would change everything, right? And so, but they're not factors. And it's not like you can factor this numerator in any way, shape, or form. It doesn't have a common factor, so you can't simplify in that shape, or in that way. Now, there is something we can do, though. Yeah, well, in a second. First, that 3 goes on here and becomes 5 to the power of 3, which is what? So write that. That becomes natural log of 125. Same with the denominator. That becomes 25. Obviously, 5 squared is 25. And then, yeah, you can use the product rule on the numerator. That becomes natural log of the product of 125 and 2. And then that's the natural log of the quotient. Now, once again, I'm not going to require you do that, but, you know, judge could have multiple choice answers, and maybe that's the answer you have to choose. Or if you want to look at a answer in the book, maybe they express it that way. I haven't checked, frankly, but some books do. So just realize you could do some work on that. Okay, like I said, I think that's the hardest thing in here. Just let me go through the steps again. First, we took log of both sides, which allowed us to move the exponents out in front as factors. And then we distributed, so we had a simplified expression, just individual terms. Factor all the x terms on one side, so factor out a common factor of x, and then divide away that, and you're done. Easy. All right, moving on. This one. what I want you to notice is you can express this first part as e to the power of x squared. Can't you? And so that's not equals. That's the trick with a problem like this, is to see that. And we normally do, we call it u substitution, because we normally use u, although you can use whatever variable you want. And so if I replace e to the power of x with u, then I have u squared minus u minus 2. And that just makes the factoring that much easier. And this is just about as easy to get as it gets. There's your factors. And so u turns out to be -1 in this case, or positive 2 in that case. And once again, we plugged in u just to make the factoring easier. So when you're done, put e to the power of x back in place of u. So you get e to the power of x equals -1 and e to the power of x equals 2. We're almost done. Questions so far? Okay. Which of those is impossible, by the way? Now you can't, look at this. If I graphed an exponential, they normally look like this. They're never 0, much less negative, right? And so this just has no solution. Actually, if I, well here, look, I'll come back to that. This one, to solve, this rewrites log problems. Log base e of 2 equals the exponent, which means you're done. That's the answer. If I tried that in this one, by the way, I'd have natural log of -1 equals x. And then that's another way you know there's no solution, because log problems have a domain that's only the positives. And so either way, you just can't do that. Okay? By the way, an equation like this that you can do u substitution so it looks quadratic. It's called quadratic in form. So it's not quadratic, but you can use your quadratic skills to solve it. All right. Same idea, but this time, what should I call u? Or e to the power 2x. So there's this first one I can rewrite as e to the power 2x squared. And that is what you're looking for this to work out, is the ability to express the very first term as the second term squared. Or at least part of the second term squared. And I say it that way because, you know, let's say it had a 5 here. Well, then you just have a 5u. Anyway, now this time, I think I'm not going to do the actual substitution. You don't have to. As soon as you see how it's laid out, you can just do the factoring. If you get a -12, you can use 3 and 4 with a -3 and a +4, right? And I'm just going to put e to the power 2x in both places. You don't have to use u, you just can help. And then set each one equal to 0 and solve. So here we get that it needs to equal 3. Here we get that it needs to equal -4. Which, once again, that one's just impossible. And this one you get log of what? Of base e, but of 3 equals the exponent. And then just type it in. Or not type it in, sorry. Take half of, and you can write it either way. You know, half of natural log of 3 or natural log of 3 over 2. And there you go, that's your answer, we're done. I'll do one little point. Like, let's say this had worked out to natural log of 2 over 2. Would that have equaled natural log of 1? No, this is not a factor of 2. You can't do that. It would just stay like this. Okay? So don't make that mistake, please. All right. That's enough of that. And there's this kind of problem. Look, you run into the situation, just run an in kind of function where you're given points on the curve. Here, the fact that they gave you the y-intercept makes this much easier. Let's just plug in. The y value goes there. The x goes in place of x as the exponent. So like to just plug in, trying to find a and b. What is n to the power 0, Caleb? N to the power 0 is 1. Yeah, no, sorry. Which means basically, you know, hey, what you might just realize that, by the way, the y-intercept is basically always that constant, because look at this, with an exponential, you start with that and then you multiply it by b multiple times. So you guys realize they gave you the y-intercept, or they gave you the coefficient, I mean. And now you go back and set it up again using the second point. So the output is negative 36. A, we now know, but B, we still don't. And what do we use for an exponent? The 2. That was the x value. And then you solve, switch signs on both sides, and you get, now listen, this equation gives you two solutions, plus or minus 6. But we're talking about base and exponential, and the base can't be negative, so actually you just get 6. Okay? And so we're not actually done. We have to write out the actual equation. So it was a is negative 1 times 6 to the power of x. You can write it down the way I said it, or just opposite of 6 to the power of x. Okay? All right, now, frankly, everything we've done up to now, that's stuff that would appear on the test. The assessment, that'll be application problems. And so, in the assessment, though, you'll have the formulas given to you, but you need to know how to choose. So here's the 4 basic formulas. For compound interest, you use these 2. For any other kind of growth decay problem, use this. If it's money, we might still use A and P, but if it's not money, then we use N, usually. And so, look, between these 2, the way you tell the difference is, basically, if it says continuously in there anywhere, then you're using one of these 2. If it doesn't say the word continuously, you're not. That's what it boils down to. Okay? And so if you look at the next example we're about to do you see the word continuous? Yes. So therefore, you're using this formula. And you can use R or K as a variable there. I like using R because then you have PERT and you have NERT. It's easy to remember NERT. Okay, let's set it up. The initial time I usually call time 0. August is how many months later? You can count your fingers if you want to. I did. Yeah. So yeah, 5. So let's set it up. The final amount was 177. The initial amount was 88. E to the power of 5. Well, R times 5. And we can solve for R. So divide by the 88 first off. And then rewrite as a log base E of the other side equals that exponent. And then just divide by 5, or you can do 1/5 of. And go and punch it in the calculator. And if you you'll get a calculator, obviously, if you didn't already do so. See if I can avoid messing it up. And I got around 0.14 for R. That isn't the final answer, though, because if you read the directions, what it wants to do is once we found R, go ahead and write the equation, or the model for this situation. And so you go back, and you want N and T to be your variables, basically. And so the initial amount, you put that number in there, E to the power of, and R was 0.14. So when we want the model, we want it to be able to find the final amount based on the time. Okay? So you make those variables again, put numbers everywhere else. Just for the record, by the way, R was 14%. Right? But in the formula, of course, you use the decimal form. All right? Frankly, that's all we're going to do on that. We're going to jump to today's notes. And we're going to start with the compound interest formula, compounded N times per year. And once again, N is going to be one of these numbers. N is 4 if it says quarterly, N is 12 if it says monthly, and so forth. That's straightforward. I said this before, just to show you again though, the more frequently it compounds, the more it grows. Maybe not a huge amount more, but more. Then look at this again. This is your compound interest formula, compounded N times per year. And I'm not going to go through all this, but if you look at the table, the point is, as n gets huge, maybe even ridiculously huge, like 10,000 times per year, is a bit much, your formula starts approaching what the compound interest formula, the continuous compound formula, would produce. And if you plug in r equals 1, that's where E came from, the actual value for E. Okay? So I'm saying again, E came from doing compound interest formulas. All right, this is your example. It's on your paper. Are we using PERT or the N formula, the one that has N in it? There you go. So I'll write out the formula. And just for the record, sometimes we put P there, sometimes we just say the initial amount. It doesn't matter what variable they use. Be careful. On this one, it's growing, so the final amount is the bigger amount. I'm just telling you, sometimes there are decay problems, and the final amount's a smaller amount. So make sure you read. Set it up. The rate, how do I express that as a decimal? Point what? 0.34. 0.34 is 34%. It's not the same. Over 12, we said is monthly. The power of 12 t. We're trying to find the time, so t is a variable. And we could solve for t. You ready? First, divide away the 5,000. Or I would cancel. Divide by 100, top and bottom. Makes it a little simpler. Now, here's the deal. You have to be cautious when you use that calculator. We've been over this a lot. So I'm going to go and type in that base. Just the base. 1 plus 0.034 divided by 12. Because I frankly just don't want to write that over and over again. You type it in and get around 1.003. And once again, I'm going to write 1.003, but I'm never going to use it in my calculations. Okay? So for now, I'm just going to let it sit there in the calculator. If I need to, I'll store it, but I don't think I'll need to. So let me just rewrite the thing, rewrite it with a base look like that, because I want to show you your two options. One option, we've been over this before, but one option is just take log of both sides. So I'm going to do log of the left side equals log of the right side, because that base is kind of horrible. And once you have log of a power formula, you can do what with the exponent? Move in front as a factor. Well, and then you're almost there. Your t has 12 multiplied onto it, and it has natural log of 1.003 multiplied onto it. So to get t by itself, divide by both of those. So you get the left side divided by, and that divided by the 12, and divided by that. And we'll type that in a second. Let me show you the other approach you could take. You could, this really is just a power form. You could write as a log. It'd be log base 1.003 of that fraction equals 12t. Now, before you do anything else, I want you to realize, if you wanted to type this in the calculator, you have to use change base formula, right? So I'm going to rewrite that using change base. It becomes log of the old argument over log of the old base. And I think you can see, take a 12th of both sides, you're in the same position, right? So either approach will get you to the same place. Now we need to get this typed in correctly. So numerator, it's easy enough. Just make sure you close parentheses. Divided by, now the base, I mean the denominator, needs parentheses around it because it's two factors. So parentheses in 12, natural log of, okay, it better still be there. I cleared memory when I shouldn't have. Well, I didn't clear memory, I just cleared the screen. The second answer should still be there. It is. I wanted to use, what was still sitting in the calculator, the thing that rounded to 1.003. Unfortunately, it was still there. You should have gotten that answer. And by the way, that is 11.1 what? Yeah. In this formula, t is always in years. And once again, I expect units on your answers. Well, perhaps, but what did you have to do to make your $2,300? Now, the bank could do the math for you. So what did you have to do? Nothing. Just give them your money for at that time, right? But that's how, when they say people are financially independent, they have the money working for them, basically, like this. You got enough money working for you, then you don't need to work. All right, now look at this. What I want you to appreciate is that I could take a situation like this, and just watch. So you have this initial amount at that rate, at this time would produce final amount. I can produce any of these four problems from that situation. If I gave you all the givens and you just ask for the final amount, that's easiest. Just plug it in, it plugs out, produces that final answer. Next easiest is where I ask for the initial amount, and I give you the final amount. Because then it's easy. You just figure out what this is and divide by that, you've got it. We just did this one where you're trying to find the time, and to find the time involves logs. This one here is also hard. These are the two hard versions. We're trying to find the time, we're trying to find the rate. Look at this. We just did this where we ended up having to do logs. And why was it necessary to do logs? Because we're trying to get rid of a base. Our variable was an exponent. And so if you're trying to get rid of a base, then it's going to involve logs. Whereas here, the variable's in the base. In other words, we're trying to get rid of the exponent. And to get rid of an exponent, use radicals. So I'm just saying, you need to know the difference. Both kinds will be thrown at you. Here, find this example. And frankly, you know, what is a zero coupon bond? Well, okay, non-interest bearing, but you don't have to be totally familiar with all the terms. You do need to get from reading this that the final amount is 1,000 and the original amount is what we're trying to find. Okay, so when you set it up, n is 12, so using that formula again, same formula. The initial amount is what we don't know. The rate was 7%, so 0.07 over 12, the power of 12 times 10 years. And this, like I said, this is easy. Just type in all that mess that's next to the p, and then divide by it after you come up with it. I'm typing in without parentheses, because I'm just going to go and take it as a two-step process. Look at the base, and now just to the power of 120. If you're going to type in all at once, of course you need parentheses. So I got round 2.01. And then divide 1,000 by that. What was that? So divided by second answer. And the next example is going to work out to around 2.01 as well. So what is it, 60 cents, 4.97, and 60 cents. And once again, if there's money, we'll round, and then there's pennies. So 2 dozen places with appropriate units. Yeah. Non-interest bearing, it says. Now you know as much as I do. All right, now, next example. Now it's continuously compounded, so we use PERT. So final amount goes there. Initial amount is what we don't know. Now it's e to the power of RT, so 0.07 times the same 10 years. We'll just do the same thing. E to the power of 0.07 times 10, which is just 0.7 actually. Type it in. And once again, you get something around 2.01. So my work's going to look the same, but in actuality it's not the same. If I do 1,000 divided by the last answer, $4.96 and 59 cents this time. And so hopefully it's clear. It required a little bit less money to start with this time because it grows faster if it's continuous. $1 and a penny. Okay. Moving on. Next example, we're going to use this formula. Once again, if it's not compound interest, then we use the other formulas. This one, it says it's continuous rate, which is why I'm using the formula I just showed you. So write that down. Inert. And set it up. We're given the final amount, plug it in. Given the initial amount. And we're trying to find the rate. On these, we'll just make time whatever they have it. On the others, time's assumed to be in years, but here it's not. So just plug it in. And start by dividing away the 120,000. And then rewrite as a log. Just would be log, natural log base E of that quotient. And then finally you divide by 126. Although I'm going to show it this way. We're going to see if I can get this thing typed in correctly this time without messing it up. So far I'm 0 for 2. This is from I'm not going to use the slate. I'm just going to type in the natural log first. And then I'm going to divide by the 126. Good, finally a success. Now, it's supposed to be a rate, and so it is 0.0305, but I want to express it as a percent around the nearest tenth. But to the nearest tenth would be 3.1. You put 3.05, that's lots. Good, except for it's not near 10. Okay? Then there's the other formula, and like I said, if it's involving money, so if it's an appreciation or depreciation problem, we usually use these variables, whereas if it's objects, population or something like that, we use n, but it's the same formula. Actually, we're going to skip that one, although, frankly, after 20 years, it was worth a lot of money. I forget what it was. It's like $1 million. And of course, you have to find someone with the money to buy it, but still. Okay. There are. This one, it's money, so we'll use A and P. Let me set up the formula first. Okay. Which one is the final amount, the 300 or the 500? Because it's depreciating, it's losing value. Like I said, read, pay attention to that detail, otherwise you'll get it all backwards and you'll kind of be wrong. And then P goes there. To start with, we'll go and divide by 500, which would just get 3/5. Now what? How do we get rid of that 5? And the logs would be the wrong answer here, because what you'd have is log with a variable inside of the log. We don't want the variable inside of log. We're trying to get the variable by itself, right? Radicals is the answer to the question. You want to use radicals. And actually, watch this. Here's your options. As far as showing the work. So like if I gave you the fifth, x to the power 5 equals 243, then one thing you could do is say, well, I'm going to take the fifth root of both sides. And that works. And this gives you x, and that gives you 3. Okay? Or you can say, I'm going to raise that to the power of 1/5. This is equivalent. So you raise both to the power 1/5, and you get the answer that way. So, which way do you want me to show the work? Aisha, sorry. I knew I said it wrong. Okay. And so I'm going to raise both sides to the power 1/5. And that cancels, so the right side is just r plus 1. And the left side was whatever that is. Type that in. And frankly, you can type it in whichever way you prefer. I'll do it the way I wrote it first. Parentheses 3/5. Power of. And with this, you don't need parentheses around the exponent. So do that. Or watch this. If you want to use radicals, we want to do the 5th root. And you do 5 and then hit the math button. Which one do we want to choose? Yeah, the fifth option there. And then I'll use, okay, what did I do? Let me try that again. 5. And then type in 3/5. And so, same thing. Type it in whichever way you prefer. And then, of course, so this works out to 0.902 or 903. Subtract 1 and you're done. You get 0.097. Now listen, the way we normally express the answer though is just 9.7%. Okay, it's negative because of depreciation, but it was 9.7% rate of depreciation. We're done. And we're actually going to stop there. Say again? Yeah, depends, but yeah, and seriously, if anyone comes to you and tries to sell you something like that and says it's an investment, no, investments appreciate in value, right?